We want to welcome you to another theory of statistics class. We got a lot to do today. All what I just need from you is pay attention. And in case you get stuck, please let me know. I'm actually going to continue from where we stopped yesterday. And of course, after this material, I'm going to go over another material. We stop at the power of a set. Now, you all know the idea behind that, but some of you may be wondering, how is this applicable in real life? You know, there's so many areas you can apply our power of a set. But before I mention the application area, what power of a set indicates is if I have elements in a set, okay, what is a possible combination of those elements? You know, we want to consider the possible combination of those elements. And that is the idea behind that. If I quickly give an example in hospital, if you take a look at what I'm displaying now, if a doctor has 3 medications, X, Y, and Z, please pay attention, okay? Doctor has 3 medication, X, Y, and Z, okay? So doctor can decide not to prescribe any of this, which is going to be empty. Doctor can decide to prescribe only just the first medication. He can prescribe the second one. He can prescribe the combination of that. He can even prescribe all of that. Do you see that now? So this is going to make the doctor to have several choices, you know, depending on how serious is the ailment. Okay, so I'm going to move from there. Now, when we're studying sets, we normally use, there's a diagram that will enable us to easily understand relationship, okay, between two or more sets. Of course, we call that Euler. We have Euler diagram, we have Venn diagram. So the two of them enable us to easily visualize relationship, you know, among sets. Now, it looks like a rectangular in shape or at times a square in shape. Take a look at what I have right now. Okay. Now, when you see there's an omega sign here, right? Oh, 1 second. I'm going to use, okay, so there's an omega sign. Okay. The omega sign is actually talking about the universal, right? Universal set. Now, when you take a look at this one, it means that set S is bigger than set T. You can see S and T; they are both uppercase, right? When you have an uppercase, it means they are set. Okay, so but one is inside the other. Okay, so set T is inside set S. Okay, so you can take that set T to be Minnesota and take set S to be United States. Okay, so take a look at that. So this is, if I want to describe this graphically, or I want to use have a visual way to understand that relationship, then I need this. And of course, if I want to write it out, then this is what I'm going to write out. If you take a look at what I have here now, so it means T is a subset of S. Now I'm moving now. Now, I want to talk about some other properties. Okay, let's talk about complement. Okay, so what complement is talking about is, I've identified the universal set. Okay, now after I identify universal set, I have another set that I'm actually going to call S. And that very set S lies in the universal set. So when I'm talking about complement of set S, it means, space outside. Outside S means I'm not interested in S. I'm not interested in S, but I'm interested in other elements within the universal set. Okay? If I'm talking about the complements of Minnesota, if United States is set S, is universal, okay? If United States is the omega is universal, okay, and set S is Minnesota. So if I'm not interested in Minnesota, then I'm interested in the other state in the US. That's what we call the complement of S. So the shaded part, take a look at the shaded part. The shaded part is the complement of this particular S, which means I'm not interested in S, but I'm interested in other sets within the universal set. Now, if I want to, if you take a look at this guy now, take a look at that. What is a complement of empty? Okay, the complement of empty is the universal set. That's what this guy is trying to talk about. What is the complement of universal set? The complement of universal set is empty. If you are not interested in the entire universal set, okay, of course, that means your interest is on empty. If you are not interested in empty, then your interest should be on the entire universal set. That's what it means. Now, whenever you see a power, that power C, we use that to denote complement. Okay, so we can actually, I can write it like this. I can do that like that. So whether I have this, a power of C, or I have this, complement. That indicate complement. And if you take a look at this guy, okay, when you have two complement of a set, then we return you back to the natural, the actual S. Okay, it's like negative. Okay, so that's what this guy is talking about. Is there any question here? Any question? Like I said, follow what we're doing now. If you don't understand, ask question. You pay for the service. Now, you now understand what we mean by the complement. The complement means not, N-O-T, not. You're not interested in a particular set S that lies in a sample space, that lies in the universal set. But if you are not interested in that, then you are interested in the remaining set within the universal set. Now, from complement, I want to go to relative complement. Let me tell you this. If you don't understand complement, then you may find it difficult to understand relative complement. Now let's go to relative complement. Okay, how do we define that mathematically? So if I want to talk about relative complement, I actually need two different sets. Okay, my relative complement is going to say, I'm interested in element from a particular set, and I'm not interested in in an element from another set. That's what relative complement means. Now, if I want to define that mathematically, please pay attention. Take a look at this guy. Okay, take a look at that. Okay, you know what that guy means? It means the random variable S I'm talking about come from T. Okay, and the random variable I'm talking about does not come from S. If I'm going to interpret that. Oh, I want to focus on the resident from Minnesota and not resident from Wisconsin. That's a relative complement. I'm interested in element from this set. I'm not interested in element from that set. That's a mathematical interpretation of what I just said right now. In the actual sense, another way I can put that, I can actually, this is the symbol. Whenever you see that, it's talking about relative complement. It means I'm interested in element from T, but I'm not interested in element from S. Another way I can put this, I can put it at T minus S. Okay, you can see which one has a minus. The set that has a minus is the one that we are not interested in. We're interested in the other one. So there are several ways we can put this. Let me tell you this. Math is easy. Math is easy. Okay? What students find difficult is to understand the story behind it, behind every notation. And that's why I'm trying to dish out now. Okay, so now you've seen the formula now. How do we now use, if I want to visualize that, please pay attention. if I want to visualize that, so how is that going to happen? Now, I need you to pay attention to what I'm actually showcasing now. If you take a look at what I have here, okay, you're actually going to see that the unshaded part, the entire unshaded part is S, right? That means I'm interested in that. The shaded part, I'm not interested in the shaded part. The shaded parts, if you take a look at what I have here, you're actually going to see that this is like a T only, okay? And if you take a look at that, so that's another way. So then another thing I'm actually going to talk about, okay? Please pay attention. You know what I mean? I'm interested in set S. I'm not interested in set S. Then I'm not interested in nothing because it's the same. It's just like somebody say, I want resident from Minnesota. I don't want resident from Minnesota. Then you don't want nothing. And that is why it is going to be empty. So which is the same thing as S minus S equal to 0. Does that make sense? There's a lot of story going on here. Please pay attention. When you relate theory of statistics, mathematics is going to be so easy. Now, but what if in a situation, take a look at this guy. Right? You know what that guy means? Okay, S relative universal set is the same thing as S minus that. Okay? It's the same thing as that. Okay, now, why do you think I said that this actually equal to empty? Okay, so why did I say equal to empty? Now, don't forget, this guy is inside this guy. If I want to reason now, I'm going to call this guy Minnesota. I'm going to call this guy United States. Okay? Now, if I'm interested, is it possible I'm interested in Minnesota and I'm not interested in United States? That's why it's going to be empty. Does it make sense? Because Minnesota belongs to the United States. Does that make sense? We can actually prove this out to show that that is equal to that. That's what I mean there. Okay, now I'm actually moving right now. Take a look at this guy. Okay? Okay, so if you take a look at that guy, S relative empty. Okay? S relative empty is like S minus empty is actually going to be S. Okay? This is empty. This has element. So it's like subtracting 0, which is still going to be that. Can you see that? That's super cool, right? Okay, so now I'm quickly going to move. What if in a situation where I want to talk about another property, because when you're talking about when you study relationship between sets, okay? We could talk about union, we could talk about interception, and something like that. We just talk about relative complement now. But right now we want to talk about union. And what do we mean by union? Please pay attention. If I give you assignment or I give you test, okay, and I want you to define union between two sets mathematically, please pay attention. Maybe I want you to define union between two sets mathematically. Now, this is the definition here. That is the definition I'm expecting. So X union T, right? S is a set. T is a set. If I want you to define that mathematically, I'm actually going to say there is this X, which is a member of this guy, a member of that set. So I'm going to say S is from that or S is from that. That's exactly what I mean. That's a union. It's like having union between residents of two states. Maybe union between residents of Minnesota and Wisconsin. Okay? So if you take a look at what I have. Now, if I'm talking about that union, that should be addition. That is pulling all of them together. That's why if you take a look at here now, everything is shaded, right? Take a look at that. Everything is shaded. I'm talking about all of that. So that is what I just gave you. You know what I just gave you now? Mathematical way of specifying union between two sets. And how do you use a diagrammatical way to visualize that? So that is what I just showed you right now. Now I'm actually moving. Okay. Now you know what is going to happen. Still on the union. If I have two sets, S union T is the same thing as T union S. Okay? Combining resident from two states. It doesn't really matter whether I start with Minnesota or I start with Wisconsin. So it's going to be commutative. Union is commutative. That's what it means. Okay? S union T is the same thing as T union S. Now, this is a situation where we're talking about two sets. We can also talk about union, okay, when we have more than two sets. And whenever we have more than two sets, we're going to call that associative. Take a look at this guy now. So maybe talking about resident from Minnesota, resident from Wisconsin, and resident from Iowa. If you take a look at that. Now, association starts from 3. That's why it's called associative. Okay? So when you take a look at what I have, you can investigate that. If I do the union between T and P, and I now, whatever I got, I do that union with S, it's going to give me the same thing as that. Okay? So you can investigate that. Now, another thing that worth investigation, please, I need you to pay attention. Take a look at this guy. If I have S union T, I have S union T, I combine the residents of Minnesota and Wisconsin together, then in the union, resident of Minnesota is a subset. Does that make sense? Yeah, that makes sense. That's what we're talking about here. Okay? I told you, maths become very interesting when you relate. That's how I understand my math. Okay? Now, I'm actually going to move to something else. Take a look at this. S union S. The same. I'm still going to have S. Right? That's what a guy means. Okay? Then I'm going to show you another one. Take a look at that. You can verify that. S union emptiness. It's still going to be S. Okay? Now, I need you to pay attention to this. Please pay attention. Okay? Look at this. Can somebody tell me? I want to use Minnesota, resident of Minnesota as an example. Can somebody interpret that one for me for extra credit? Can somebody interpret that? Okay, go ahead.
You're saying that, like, a set of residents of Minnesota,
Yeah.
the union of sets of every other state
Okay.
besides Minnesota,
Okay.
the union between them is
Yeah.
equal to the United States.
That is it. Send me a message for extra credit. So S is the resident of Minnesota. S complement is not resident of Minnesota. Not resident of Minnesota will be resident of other state. When I put them together, that become United States. Thank you so much for that. Okay, I'm moving. Okay. Take a look at this guy. Oh, Minnesota Union United States. I'm adding Minnesota to United States. Of course, I'm going to get United States. That's what that guy means. Now, I want to generalize now. Let's generalize now. Okay, so I want to generalize now. Take a look at this. Oh my God. Initially, I've been talking about union between two sets, but right now, I want to generalize to more than two sets. Maybe I'm talking about the union of every state in the United States. X1, Minnesota, S2, Wisconsin, S3, Michigan, and so on like that. Take a look at that. So if you take a look at what I just circled now, please pay attention. We are getting into a complicated, situation in this course. Okay? But you know what? It's not going to be complicated if you understand what its notation represent. Now, right now, I want to be able to write something in a short form, but what am I doing? I want to have union of several sets. I want to have union of several sets. X1 union, X2 union, X3 union, X4, and that continue to go to Xn. Where n here represent the number of sets I'm talking about for United States. If I'm talking about state, that will be 50. Now, if I don't want to write it this way, okay? If I don't want to write it this way, what is the shortest way to write this? The shortest way to write this, I'm actually just going to write that guy. Then I'm going to do I start from 1. I'm going to put this guy here, then I'm going to put SI. Look at that. This is the shortest way of writing all of this, which means I got SI. I start from 1 to n, which means if I plug in 1, it's going to be x1, junior x2, and so on like that. So this guy is the shortest way to write this. Okay, which is what you're seeing here. Any question? If you just see stuff like this, you're going to be asking yourself question, what is the meaning of this? Oh, this is hard. This is not hard. When you relate this, you're actually going to be fine. So this is like a union of several sets, like several sets coming together. Now, I want to leave union right now. I want to go to interception. Our intention with union is different from our intention with interception. Of course, with intersection, what we actually want to figure out, can we have something at the center? Can we have something common to set? That's what we mean. Now, I want to go into interception now. Okay, we are here now. Okay, but I need you to pay attention. If I give you an assignment, define interception of two sets mathematically, how are you going to define that? This is what I'm expecting. This is what I'm expecting here. All the way here. And let me tell you what I'm going to do. S interception T. I need to first say that. Equal, you're going to write S such that S is from S and S is from T. What is the difference between this and that of the union? The only difference between that and that of the union is conjunction use. The conjunction used for interception is going to be A and D, and the conjunction used for union is actually going to be or. If you check the definition for the union, please pay attention. Take a look at this. Do you see the conjunction use? That is the only difference. S comes from S or S comes from that. Or that's for the union. Do you see that? It's conjunction. So when I talk about interception now, that very OR is going to change to A and D. That's a mathematical way of defining interception of two sets. Now, if I now want to use a Venn diagram, if I want to use a diagram to do that, so the shaded part is the common. What is common between them? Look at that. That's what's common, right? You see that? That's what is common between them. And that's what we mean by the interception. Is there any question? Any question? Okay. So, somebody's going to say, oh, if I want to interpret this, I'm going to say, maybe what a resident of Minnesota like and what a resident of Wisconsin like at the same time. So, okay, now I'm moving now. I'm going to move now. Now, I'm now going to have the same way that we have so many properties on union the other time. We're also going to have properties on interception. And we're also going to generalize the way we generalize union for union the other time. We're also going to generalize for interception. But let's first take a look at, let's investigate commutativity. So take a look at that. The common between S and T is the same thing as the common between T and S. Imagine I ask you to write the definition for this mathematically. Okay, so they're going to be commutative. Then they're also associative. Okay, you know the union is associative, intersection is also associative. You take a look at that. Okay, so another thing we also find out is this. Okay, another thing we find out is this. And I need you to pay attention. I want you to reason with that. If you don't understand what is behind your reasoning, please let me know. I'm actually going to explain. Now I have S and T, right? The common between S and T, okay, that very common belong to T. How do I know belong to T? Let's take a look at this. Okay, what is the common between S and T here? The common is here, right? The common between this is here, right? What does it belong to? It also belongs to T. Can you see that? And at the same time, it also belongs to X. Can you see that? Okay, so that's what I mean. Now, what about the same thing here? You know, when you take a look at this too, it belongs, the common between S and T belongs to T. The common between S and T also belongs to S. Okay, now, oh my God, what about the common between set S and set S? What is common between resident of Minnesota and resident of Minnesota? It's Minnesota. Okay, that's what I say. Okay, and when you talked about intersection between residents or between a set S, what is common between a set S and an empty set? What is common between set S and empty set is actually the set S itself. Okay, and what is common between? If you take a look at this guy here, what is common between set S and an empty set? You know, when you take a look at the difference between this guy and this guy, let's pay attention. What is the first one? What is common between Minnesota and United States? What is common between there is Minnesota. Does that make sense? But the second one is saying, what is common between Minnesota and nothing? Okay, what is common between Minnesota and nothing is the emptiness itself. Okay, now I want to go into generalization. The other time we have X1 union. I actually want to change this to interception. It's just like, what is at the point of intersection of all states, all sets? Okay, this guy, that guy. Okay, the only thing I'm actually going to do, I'm also going to change this guy. I'm going to change this guy. Can you see that? So now, this is the shortest way of writing this. Okay? So, which means we want to focus on what is common between all the sets together. Okay? Can somebody tell me here, what do you think is common between all states in the United States? Has anybody traveled to all states in the United States? Can I see your hands up if you have traveled to all the 50 states in the U.S.? All 50 states in the U.S. 49. What about 49? 48. 40. 30 states. 30 states. Good job. What do you find common, between all the 30 states that you've traveled to?
People, their cities.
Okay, you see, at least you're gonna, when you are traveling, there's something that you have in mind, like, oh, this is common, and there's something you're also gonna have in mind that, oh, this is different from the way they do in the other. I remember when I traveled to New York with my kids, I was like, oh my God, this is too fast compared to Minnesota here. Okay, thank you so much for sharing that. Okay, let's move. Take a look at this. I want to demonstrate. So I think I've worked on that. That makes sense. Now, I want us to talk about symmetric difference. But let me tell you this. Please pay attention. Before you can understand symmetric difference, you need to first understand relative complement. Because symmetric difference has to do with relative complement. So I want to walk you through now. Now, take a look at this. We're working on this right now. Okay? I have two sets. But you know what I want to do? I actually want to look into symmetric difference between the two sets. Symmetric difference, what is the notation? Okay? If I want to talk about, this is a notation. At times when you look into some textbook, you're going to see this. Okay? We can use that notation as well for symmetrical difference. But let me tell you this. Do you know symmetric difference is a union of two relative complements? Okay? So this guy is actually this union, this. This is a relative complement. It's another relative complement. The union of the two is actually going to give a symmetric difference. So which means this guy, T minus S, union X minus T. That's what we mean. Take a look at that. This is relative complement. The union of relative complement is a symmetric difference. And that is what I'm trying to show here. That's what you see here. Take a look at that. Look at that. Okay, the union of S minus T, S minus T, union T minus S. Go ahead.
Triangle the same as the symmetric.
Exactly. So this we can use any of this notation for symmetric. Okay, you can use a triangle. When you look at some textbook, you're going to see that. So in this course, if I want to ask a question, if you want symmetric, the moment you say this or that, so I mean symmetric difference. Does that make sense? Okay, now I need you to pay attention now. When I'm talking about, if you take a look at this, do you know what this guy is saying? It's trying to say T only. T only. Okay? Now, let's go and see where is T only. This is T only, right? Okay? Then, what is S only? This is S only, right? When I add this to this, that's a symmetric difference. The unshaded part is not needed. That's what we mean here. The union here is actually telling you, add them up. That's what union talk about. Add them up. Okay? So that's what you see here. Okay, now I want to walk you through properties of symmetric difference. Now you know how to get symmetric difference. I've seen a lot of assignment here. Of course, I'm releasing assignment 1 on Sunday. Okay? So I'm seeing a lot of assignment here. Now take a look at this. Symmetric is commutative. That's what I mean. If I find S symmetric T is the same as T symmetric S. So it's actually commutative. Okay? And it is also associative. That's what this guy is talking about. It's associative. Do you know I can give you an assignment, I can give you some sets in S, some sets in T, some sets in P, and I can ask you to investigate that associative relationship to see whether that hold. I can ask you to investigate commutativity. Okay? I can give you, I'm going to give you some elements in that. Now, if you take a look at this one, now let's talk about this one. Hess symmetric emptiness is actually Hess. And when you do symmetric difference of the same set, it's empty. Symmetric difference of the same set is empty. Okay? So that's what that guy is talking about. Now, I want to move into something else. Any question for me? Any question for me? Make sure when you are in my class, pay attention. My experience in teaching at this level for 15 years when students bring laptop to class, maybe they are doing something else. Are you sure you're not doing something else? You sure? Let me see. Good job. Good job. Good job. Good job. Don't do something else. Good job. Good job. I can see that. Don't do something else. Good job. I can see what you're doing. Okay? Please be focused. Okay? Because summer semester is very short. Before you know, we're going to have exam. Right? We're going to have exam. So make sure you be focused. Anyone in this class who has a troubled time with the way I talk? Anyone? Okay, I remember when I stepped into this country for the first time in 2013, when I touched down in Houston, Texas, you know, my accent wasn't like this, so I keep on improving by the day. So if you having a trouble time understanding the way I talk, please let me know. Okay, so let's go to partition of a set. Okay, you know, of course, because we can't be in the same geographical zone. There's variation in the world. There's always going to be partition by boundaries, and so on like that. So I want to walk us into partition now. Take a look at this. That's an example of partition. Okay, where I'm going to say, oh, this is for set A, this is for set C, that's for P. But when I combine all the set, then I'm actually having universal set. Okay. Now we need the idea of partition work when we want to talk about Cartesian products. Now let's talk about Cartesian products. Okay. You know, by Cartesian products, we actually want to focus on, the product of several pairs. Okay. And I'm actually going to walk you through that now. So let's take a look at this. We want to focus on this guy now, Cartesian products. And you're going to ask me, what notation? If I want you to find a Cartesian product between set S and T, what would be the notation between set S and T? It's actually going to be what you know. Take a look at that. Look at that. You see that? It's just going to be S times T. Okay? So notation, different information. You remember the other time when you see this guy? I said symmetric difference. When it is minus, that would be relative complement. Okay? But now, when I put a cross, like a multiplication sign, that becomes Cartesian products. Okay, so now how do we define Cartesian products? And I need you to pay attention. I'm going to give you an example. Okay, so let me quickly give you an example. If I have a set S, okay, if this is set S and this is set T, okay, now I want to find Cartesian products. Please pay attention. Okay, the order do matters here because I want to use this to multiply that. So I'm going to consider XA, okay, XB, okay, YA, YB. Do you see that? That's a Cartesian product. Okay? And let me tell you this. The cardinality here is 2. The cardinality means how many elements do I have here? The cardinality here is actually 2. Obviously, the cardinality of this has to be 4. Because you know why? The cardinality of this guy must be equal to the cardinality of that multiplied by that. 2 times 2. What is 2 times 2? That's 4. That's why 1, 2, 3, 4. Okay? That's a Cartesian product. But if I want to get T multiplied by S, that will be different. Then I'm going to start from the other one. So I'm actually going to have AS, okay, AY, okay, BS, then BY. Okay, you know what? This guy is not the same as this guy. So which means, as far as Cartesian product is concerned, commutativity doesn't work. And that's why, take a look at it. That's what I'm talking about here. Okay? But we can have situation where commutativity is gonna work. Can somebody give me the situation where commutativity is gonna work for Cartesian products? Yeah. What is the situation where s multiplied by t will be equal to t multiplied by s? Exactly. If they have the same elements, same EMSs or extra credit. I don't joke with my extra credit. Imagine somebody had 20 points and the person scored 80% in the final. The person can say, can you add my 20 to 80? The person will just get 100% in the final. I don't joke with my extra credit. Okay, thank you so much. Now, and that was why I said, look at the condition. This is not equal to this if they are not equal. But if they are equal, for instance, I have the same element. If this is A and B, and this is also A and B, of course, I'm actually going to have that multiplied by that will be that multiplied by that. But the moment they have different elements, the commutativity doesn't work. Okay. Now, if commutativity doesn't work, if they don't have the same element, then associative is not going to work. That's what I mean by this guy. Can you see that? If commutativity doesn't work, associativity is not going to work. That's what I mean by that guy. Now, lastly today, I want to go into this. And I need you to pay attention now. Do you know we can actually hide under what we've known, for us to be able to understand De Morgan's theorem? Okay? Now, let me give you De Morgan's theorem. This is the general De Morgan's theorem. Okay? This is the first De Morgan's theorem. This is the second De Morgan's theorem. And I need you to pay attention. I know this is looking complicated. But you know what? I'll first start from two events. Okay? I'm actually going to start from two events. I'm going to start from two events. Okay? Now, x1 union s2 complement, okay, is equal to x1 complement intercept s2 complement. This is the fourth De Morgan's law when I'm talking about two sets. Okay, the second De Morgan's law, is x1 intercept s2 complement is the same thing as x1 complement union s2 complement. I need you to pay attention. Okay? It's like we've already verified this. If I have two sets, please pay attention. If I have two sets, I find the union, and after finding the union, I take the complement. Okay? That means I'm interested in outside. I'm not interested in the x1 and s2. That's what I mean. It is the same thing as the interception of the complement of H. Now, this is for two event situation. Definitely for so many event situation, I'm actually going to talk about this guy. You know what this guy means, right? x1 union s2 union s3 until you get to xn, the complement of that. So this guy here is a generalization of this guy. This guy here is a generalization of this guy. Okay? This guy here, the complement of all the interception is a generalization of this guy. This guy here is a generalization of this guy. Okay? Now, let's take a look at this. The union of this guy equal to that. Now, I'll quickly give you an example in real life. Let's go to medical line. And let's see what example is. Has anybody heard about clinical trial? Now, in clinical trial, when they are trying to recruit and they actually want to select any individual for control groups, and they said they don't want individual with underlying conditions. They don't want somebody that have diabetes, and they do not want somebody that have hypertension. You know what I mean? That means they don't want neither. That's what it's saying. Neither of that. This actually compliment mean neither. If they don't want neither, you know what it means? It means no diabetes, no hypertension. No that. That is a compliment. Does that make sense? Now, I'm going to go into another example now. Okay? For this. To get into a building. Okay, it's either your ID card is valid, right? And your password is correct. Okay? So which means you're going to be denied access if any of that is not right. So that's what this guy is talking about. Okay? So now I'm actually going to derive this for you. But I'm expecting you to derive the second one yourself. That become an assignment. So let me quickly use my time to derive the first one. Please pay attention. Okay? Pay attention. This is the first De Morgan's theorem. If I want to derive this, okay, I'm actually going to say S lies in that. Right? S lies in that. If S lies in the complement of that, then it means S does not lie in this. Do you see that? Please pay attention. If S lies in the complement of that, then it means S does not lies in that. If S does not lie, okay, if I want to interpret this, okay, I'm actually going to write X. That means I have this guy for this, and this guy for this. Please pay attention. Because this guy actually means that guy. Now, you know what I want to do now? If I want to rewrite this guy is going to be complement, and this guy is going to be complement. Can somebody tell me, when I have A and D, you remember the other time? Conjunction A and D is going to form an intersection. So this guy now is actually going to be X1 complement intersect S2 complement, so which means S lies in this. So what does that mean? So this is equal to that. This is equal to this. That's what I mean. That's how we know that that's equal to that. Done. I'm done. Look at that. I'm going to say that again. We want to prove that this is equal to that. S belongs to that. We start from here. If S comes from the complement of that, then S does not come when I remove complement. When I have this, I can split that. This guy means S does not lie in that and S does not lie in that. And here, if I want to remove this is going to have a complement. Then because I have A and D, then I'm combining. A and D, we actually imply intersection sign. I need you to prove the second one. Try the second one. The second one is the one I gave the other time. Okay? The second one is this. Okay? This is the second De Morgan theorem. Okay? This is very useful in medical field, useful in engineering. In fact, in computer programming. If you take a look at this guy in Python programming will mean not X1 and S2. Not X1 and S2 in Python programming mean not X1 or not X2. If I want to write that in Python programming, okay, in Python programming, okay, not X1 and S2 actually mean not x1 or not s2. That's what I have for you today. Make sure you all stay safe and have a lovely day. See you tomorrow.